Bioremediation and phytoremediation. Bioremediation. Waste products resulting from human life have always been a serious problem. Today, these waste products ranges from a raw sewage to nuclear waste. To cope up with these bioremediation seems to be a good alternative to conventional cleanup technologies research in this field, with which ultimately causing a rapid growth in this field. The bioremediation is not a new technology. These have been evidence that compost piles existed as far back as 6000 BC, and in 1891 the first biological sewage treatment plant was created in Sussex, USA. However, the word bioremediation did not appear in the reviewed scientific literature until 1987. Bioremediation is the use of living organisms, primarily microorganisms, to degrade the environmental contaminations or biological degraded under controlled conditions to an innocuous state to level below concentration limit established by regularly authorized. It uses microorganisms for degradation of a hazardous chemical in soil, sediments, water, or other contaminated materials. Often, the microorganisms metabolizes the chemicals to produce carbon dioxide or methane, water, and biomass. Alternatively, the contaminants may be enzymatically transformed to metabolites that are less toxic or innocuous. It should be noted that in some instances, the metabolites forms are more toxic than the parent compound. For example, perchloroethylene or trichloroethylene may degrade to vinyl chloride. Apart, bacteria, fungi, algae, and plants have also been used for result of action of multiple organisms. When microorganisms are imported to a contaminated site to enhance dehydration, we have a process known as bioaugmentation. Bioremediation is very safe because it relies on microbes that naturally occurs in soil. These microbes are helpful and posed to treat to people at the site or in community. The microbes themselves won't hurt you, but never touch the polluted soil or underground water, especially before eating. No dangerous chemicals are used in bioremediations. The nutrients added to make microbes grow or fertilizer commonly used on lawns and gardens, because bioremediation changes the harmful chemicals into water and harmless gases. The harmful chemicals are destroyed. The bioremediation has been used at a few sites worldwide, including Europe, with a varying degree of success. The techniques are improving as greater knowledge and experience is gained, and there's no doubt that bioremediation has great potential for dealing with certain types of site contamination. Like other technologies, the bioremediation has its limitations, as bioremediation can be effective only where the environmental conditions permits microbial growth and activity. Its application often involves the manipulation of environmental parameters to allow microbial growth degradation to proceed at a faster rate. Microbes used for bioremediations: D. Deinococcus radiodurans bacteria have been genetically modified to digest solvents and heavy metals, as well as toluene and ionic mercury from highly radioactive nuclear waste. Geobacter sulfurreductans bacteria can turn uranium dissolved in groundwater into a non-soluble collectible forms. Dihalococoides ethanogens bacteria are being used in 10 states to clean up chlorinated solvents that have been linked to cancer. The bacteria are naturally found in both soil and water and can digest the solvent much faster than using the traditional cleanup method. An enzyme from Bacterium thermus bronchianus found in Yellowstone National Park breaks down hydrogen peroxide 80,000 times faster than current chemical in use. The bacterium Alcaligens eutrophus naturally degrades 2,4-D, the third most widely used herbicide in USA. Most bioremediation systems are run under aerobic conditions, but running a system under anaerobic conditions may permit microbial organisms to degrade otherwise recalcitrant molecules. For microbes to clean up harmful chemicals, the right temperature, nutrients, fertilizers, and amount of oxygen must be present in the soil and groundwater. These conditions allows the microbes to grow and multiply and eat more chemicals. When conditions are not right, the microbes grow too slowly or die, or they can create more harmful chemicals. The control and optimization of bioremediation process is a complex system of many factors. The time that is taken to bioremediate a site depends on several factors. 1. Type and amount of harmful chemical present. 2. Size and depth of the polluted area. 3. Type of soil and conditions present. 4. Whether cleanup occurs above ground or underground. These factors vary from site to site. It can take a few months or even several years for microbes to eat enough of the harmful chemicals to clean up the site. Environmental condition affecting degradation. Parameters: soil moisture, condition required for microbial activity 25 to 28% of water holding capacity, optimum value for an oil degradation 30 to 90%, soil pH, condition required for microbial activity 5.5 to 8.8, and optimum value for an oil degradation 6.5 to 8. Oxygen content, aerobic, minimum air filled pore space of 10%, optimum value for an oil degradation is 10 to 40%. Nutrient content, the condition required for microbial activity, N and P for microbial growth, optimum value for oil degradation, C is to N is to carbon is to nitrogen is to phosphorus is equal to 100 is to 10 is to 1. Temperature, natural required condition required for microbial activity 15 to 45 and degree centigrade. Optimum value for an oil degradation is 20 to 30. Contaminants, the condition required for microbial activity not too toxic, and the optimum value for an oil degradation of contaminant, hydrocarbon 5 to 10% of dry weight of soil 700 ppm. Heavy metals, the condition required for microbial activity total count 2000 ppm. The type of soil, the condition required for microbial activity low clay or slit content. Bioremediation is being classified in many classes based on various parameters. Based on the type of degradation procedure, bioremediation can be classified into three classes. 1. Biotransformation, the alteration of contaminant molecules into less or non-hazardous molecules. 2. Biodegradation, the breakdown of organic substances into smaller organic or inorganic molecules. 3. Mineralization, it is the complete biodegradation of organic molecules, organic materials into inorganic constituents such as carbon dioxide or H2O4. These three classification of bioremediation can occur either in situ at the site of contamination or ex situ, the contamination taken out of site of contamination and treated elsewhere. Based on the type of organism used, the bioremediation can also be broken down into 4 categories: bacterial remediations, mycoremediation, phytoremediation, and compost bioremediation. 1. Bacterial remediation. The bacterial remediation is the process of using bacteria to break down molecular contaminant like hydrocarbon into simpler, safer component. 2. Mycoremediation and phytoremediation. The mycoremediation and phytoremediation is the process of using fungi and plant respectively to break down molecular molecular contaminants like into simpler, safer components. The compost bioremediation. The large number of beneficial bacteria can be introduced into the soil by brewing something called compost tea, or through use of product called efficient microorganisms. The compost tea is a water-based, oxygen-rich culture containing large pollutions of beneficial aerobic bacteria, nematodes, fungi, and protozoa, which can be used to bioremediate toxins. It is made by adding an inoculant and food source to non-chlorinated water and aerating it. The microorganism present in the inoculant rapidly multiplies when put in oxygen-rich water with ample food. This brew is applied to contaminated soil where the microbial population go to work breaking down certain type of molecular contaminant. The easy and low cost of making compost milk, compost tea, makes it a method of bioremediation with potential for widespread application. Bioremediation strategy. The different techniques are employed depending on the degree of saturation and aeration of an area. In situ bioremediation. The in situ technique are defined as those are applied to soil and underground at the site with minimal disturbance. The bioremediation technology that are used in place without removal of contaminated matrix. Both intrinsic and engineered bioremediation technology can be used in situ. These techniques are generally the most desirable option due to lower cost and less disturbance, since they provide the treatment in place, avoiding excavation and transport of contaminants. In situ, these techniques are generally the most desirable option due to lower cost and less disturbance, since they provide the treatment in place, avoiding the excavation and transport of contaminants. In situ treatment is limited by the depth of soil that can be effectively treated. The most important land treatment or bioventing. Bioventing is the most common in situ treatment and involves supply air and nutrient through wells to contaminate soil to stimulate the indigenous bacteria. Bioventing employs low airflow rate and provides only the amount of oxygen necessary for biodegradation while minimizing volatilization and release of contaminants to the atmosphere. It works for simple hydrocarbons and can be used where the contamination is deep under the surface. In situ biodegradation involves supplying oxygen and nutrient by circulating aqueous solution through contaminated soil to stimulate naturally occurring bacteria to degrade organic contaminants. It can be used for soil and groundwater. Generally, this technique includes the conditions such as infiltration of water containing nutrient and oxygen or other electron acceptor for groundwater treatment. Porging involves the injection of air under pressure below the water table to increase groundwater oxygen contaminations and enhance the rate of biological degradation of contaminants by natural occurring bacteria. The biosporing increases mixing in the saturated zone and thereby increase the contact between the soil and groundwater. The easy and low cost of installing small diameter air injection point allows considerable flexing in the design and construction of the system. Bioremediation frequently involves addition of microorganisms, indigenous or exogenous, to the contaminated sites. Two-factor limits the use of added microbial culture in a land treatment unit. 1. Non-indigenous culture rarely compete well enough with an indigenous population to develop and sustain useful population level. 2. Most soil with long-term exposure to biodegradable waste have indigenous microorganisms that are effective degrades if the land treatment unit is well managed. Ex situ bioremediations. The bioremediation technology that requires removal of the contaminated matrix by excavation, so it can be manipulated in some way by using slurry reactor, composting, biopiles, or other technology. Ex situ techniques are those that are applied to soil and underground or the ex situ techniques are those that are applied to soil and groundwater at the site, which have removed from the site via excavation, soil, or pumping water. Bio-augmentation technique involves the addition of microorganisms with the ability to degrade pollutions. These techniques involves the excavation or removal of contaminated soils from ground. Land farming. The land farming is a simple technique which is contaminated soil is excavated and spread over a prepared bed and periodically tilled until pollutants are degraded. The goal is to stimulate indigenous biodegradative microorganisms and facilitate their aerobic degradation of general. The practice is limited to the treatment of contaminants. In general, the practice is limited to the treatment of superficial 10 to 35 centimeter of soil, since land farming has the potential to reduce monitoring and maintenance cost as well as clean up liability. It has received much attention as a disposal alternative. Composting is a technique that involves combining contaminated soil with non-hazardous organic amendments such as manure or agricultural waste. The presence of these organic materials supports the development of rich microbial population and elevated temperature characteristics of composting. Biopile. Biopile are the hybrids of land farming and composting. Essentially, engineered cells are constructed as aerated composted piles, typically used for treatment of surface contamination with petroleum hydrocarbons. They are a refined version of land farming that tends to control physical loss of contaminants by leaching and volatilization. Biopile provides a favorable environment for indigenous aerobic and anaerobic microorganisms. Bioreactor, slurry reactor, or aqueous reactor. Bioreactor, slurry, slurry reactor, or aqueous reactor are used for ex situ treatment of contaminated soil and water pumped up from a contaminated plume. The bioremediation is in bioremediation in reactor involves the processing of contaminated soil, sediment, and sludge or water through a engineered contaminated system. The slurry bioreactor may be defined as a containment vessel and apparatus used to create a three-phase solid liquid and gas mixing conditions to increases the bioremediation rate of soil-bound and water-soluble pollutants as a water slurry of the contaminated soil and biomass, usually indigenous microorganisms capable of degrading target contaminant. In case the rate and the extent of biodegradation are greater in bioreactor system, that is in situ or in solid phase system, because the contained environment is more manageable and hence more controllable and predictable. Despite the advantage of reactor system, there are some disadvantages. The contaminated soil requires pre-treatment. Example, excavation or alternative. The contaminant can be stripped from the soil via soil washing or physical extraction. Example, vacuum extraction before being placed in a bioreactor. Other remediation technologies. Intrinsic bioremediation. Often bioremediation can be accomplished without intervention by microorganisms that are naturally found in the contaminated matrix. For this approach to be used, it is usually necessary for the rate of contaminated degradation to exceed the rate of contaminant migration. The knowledge of following key site characteristics are required to evaluate the likely success of intrinsic remediation. The availability of a contaminant, likely of nutrients, the presence of minerals to buffer the pH of matrix, adequate level of electron acceptor, either oxygen, nitrate, ferric ion or sulfate, and site specific contamination migration rate. B. Engineered bioremediation. In some cases, it may be desirable to construct engineered system to supply nutrient, electron acceptor or other materials that enhances the rate or extent of contaminant degradation. This is desirable when the rate of contaminant migration, the location of environmental receptor or other liability issues dictates that steps to be taken to optimize the rate of contaminant degradation in order to mitigate contaminated migration. The key site characteristics for engineering biodegradation are the same as for intrinsic remediation. However, in addition, it is important to consider factors that affects the ability to introduce chemical to the environment, such as the permanently of the soils or subsurfaces, uniformity of the subsurface. See, combination of technologies. The non-biological treatment technologies or source removal may be used to reduce the total amount of contaminant present at the site before or concurrent with bioremediation. For example, excessively contaminated soil may be excavated at the source of contamination. Volatile contaminants may be vacuum extracted, or undissolved pool of contaminants may be pumped from aquifers. Summary of a bioremediation strategy. Technologies in situ. Example, in situ bioremediation. Benefits: most cost efficient. Limitations: environmental constraints. Factors to consider: biodegradable ability of indigenous microorganisms. Technology in situ example, biosporging. Benefits: non-invasive. Limits: extended treatment time. And factors to be considered: presence of metals and other inorganics. Technology in situ bioventing, bio bioaugmentation. Benefits: relatively passive, natural attenuation. And bioaugmentation, natural attenuation process, treats soil and water. And limitation: monitoring difficult. Factors to be considered: environmental parameter, biodiversity of pollutants, chemical solubility, geological factors, distribution of pollutants. Technology ex situ. Examples: land farming, cost efficient, space and limitation, space requirement. And in case of ex situ, examples: composting, low cost, and limitation, extended treatment time. And technology ex situ biopile. Benefits: can be done on site. And limitation: need to control abiotic loss, mass transfer problem, and bioavailability limitations. Bioreactor. Next technology, bioreactor. And the example: slurry reactor, aqueous reactor. Benefits of slurry reactor: rapid degradation kinetics. Limitation: soil requires excavation. And bioreactor technology. Example: aqueous reactor. The optimize environmental parameter, enhance mass transfer, and effective use of inoculant. And limitation: relatively high operating and toxicity of amendments. In case of In case of bioreactors, the benefits of aqueous reactor, effective loss of inoculant, and it is cost and toxic, and factors to be considered: toxic concentration of contaminant. Potential advantages and disadvantages of bioremediation. The use of intrinsic or engineered bioremediation process offers several potential advantages that are attractive to site owners, regulatory agencies, and the public. These includes advantages of bioremediation. Bioremediation is a natural process, and it is therefore perceived by the public as an acceptable waste treatment process for contaminated materials such as soil. The microbes able to degrade the contaminant increase in number when the contaminant is present. When the contaminant is degraded, the biodegradative population declines. The residue for the treatment are usually harmless products and includes carbon dioxide, water, and cell biomass. A. Theoretically, bioremediation is useful for complete destruction of a wide variety of contaminants. Many compounds that are legally considered to be hazardous and can be transformed to harmless product. This eliminates the chance of future liability associated with the treatment and disposal of contaminated material. B. Instead of transferring contaminants from one environment medium to another, for example, from land to water or air, the complete destruction of target pollutant is possible. C. Bioremediation can often be carried out on site, often without causing a major disruption of normal activity. This often eliminates the need to transport quantities of waste off site and potential threat to human health and the environmental that can arise during the transportation. D. Bioremediation can prove less expensive than other technologies that are used for cleanup of hazardous waste. Disadvantages of bioremediation. Bioremediation is limited to those compounds that are biodegradable. Not all compounds are susceptible to rapid and complete degradation. There are some concerns that the product of biodegradation may be more persistent or toxic than the parent compound. See, the biological process are often highly specific. Important site factors required for success includes the presence of metabolically capable microbial population, suitable environmental growth conditions, and appropriate levels of nutrients and contaminants. D. It is difficult to extrapolate from bench and pilot scale study to full scale field operations. E. The research is needed to develop and engineer bioremediation technologies that are appropriate for site with a complex mixture of contaminants that are now eventually dispersed in the environment. The contaminant may be present as solid, liquid, and gas. F. The bioremediation often takes longer than other treatment options, such as excavation and removal of soil or incineration. G. Regulatory uncertainty remains regarding acceptable performance criteria for bioremediation. There is no acceptable definition for clean evacuating performance of bioremediation is difficult, and there is no acceptable endpoint for bioremediation treatment. Some of the commercial available and patented bioremediation process were used worldwide or described here. Two-step static system. Two-SIM is a two-stage solid phase bioremediation technology that involves both aerobic and anaerobic treatment stage. In the first stage, the explosives contaminated soil is combined with a carbon source, an inoculum, vitamin, and water to achieve anaerobic condition. The resulting mixture is formed into a static pile or placed in a bermed constructions or box to facilitate the chemical reductions of aromatic and nitramide explosives. In the second stage, the anaerobically treated soil is combined with the yard waste compost and built into a aerated biopile. The biopile may be aerated by forced air conveyed through perforated piping buried within the pile or by turning the pile with a compost turner. The previous testing of TOSIM has demonstrated the TNT removal efficiency of less than 99%. 2. Bio in a box SM. Bio in a box SM is a waste management process for remediating petrochemical contaminant soils in quantities of 1,000 cubic yard or less. In this process, the contaminated soil is moistened, mixed with the nutrients and custom growth microorganisms and then placed in enclosed containers called solid phase bioreactors for incubation. These containers may or may not be linked to aeration and vacuum pump depending on the contaminants being processed. In just a few weeks, the contaminated soils will be ready for landfill disposal or reintroduction into the environment. Next, the biosite SM system. The biosite SM system is waste management proprietary system for the large-scale bioremediation of soil contaminated with petrochemicals, including but not limited to 1. Acetone, 2. Benzene, 3. Toluene, 4. Methyl ethyl ketone, 5. Methyl isobutyl ketone, 6. Petroleum hydrocarbons, 7. 2 and 3 ring PAS, 8. Alcohols, 9. Ethyl benzene, 10. Xylene. In bioscitism system can also handle other contaminants including A. Aliphatic chlorinated hydrocarbons, example trichloroethylene. B. Spent molecular sieves from packaging towers. C. Chemical manufacturing waste. And D. Pesticides. The DDT contaminant soils may be treated using the Xenormi bioremediation process licensed from AstraZeneca. Phytoremediation. Although the applications of microbiotechnology has been successful with petroleum-based constituents, the microbial digestion has met limited success for widespread residual organic and metal pollutants. The vegetation-based remediations shows potential for accumulating, immobilizing, and transforming a low level of persistent contaminants. In natural ecosystem, plants acts as filters and metabolize substances generated by nature. The phytoremediation is an emerging technology that uses plants to remove contaminants from soil and water. The term phytoremediation is relatively new, coined in 1991. Its potential for encouraging the biodegradation of organic contaminants required further research. Although it may be a promising area for future, the phytoremediation is well studied for use at a very large field sites where other methods of remediations are not cost effective or precisible. At sites with a lower concentration of contaminants where only polished treatment is required over a long period of time, and in conjunction with other technologies where vegetation is used as a final cap and closure of the site. There are some limitations to the technologies that is necessary to consider carefully before it is selected for site remediation. The longer duration of time for remediation, potential contamination of vegetations and food chain, and difficulty establishing and maintaining vegetations at some sites with high toxic level. We can find 5 types of phytoremediation techniques classified based on the contaminant fate. Phytoextraction, phytotransformation, phytostabilization, phytodegradation, rhizofiltration. Even if a contaminant of these can be found in nature. 1. Phytoextraction or phytoaccumulation. It is a process used by the plant to accumulate contaminant into the root and above ground shoots or leaves. This technique saves tremendous remediation cost by accumulating low level of contaminants from a widespread area. Unlike the degradation mechanisms, this process produces a mass of plant and contaminants, usually metals, that can be transported for disposal or recycling. 2. Phytotransformation or phytodegradation. It refers to the uptake of organic contaminants from soil, sediments, or water, and subsequently their transformation to more stable, less toxic, and less mobile form. Metal chromium can be reduced from hexavalent to trivalent chromium, which is a less mobile and non-carcinogenic form. 3. Phytostabilization. It is a technique in which the plant reduces the mobility and migration of a contaminated soil. Leachable constituents are observed and bound into the plant's structure so that they form a stable mass of plant from which the contaminant will not re-enter the environment. 4. Phytodegradation or rhizodegradation. It is the breakdown of contaminant through the activity existing in the rhizosphere. This activity is due to the presence of protein and enzyme produced by the plant or by soil organisms such as bacteria, yeast, and fungi. Rhizodegradation is a symbiotic relationship that has evolved between plant and microbes. The plant provides nutrients necessary for microbes to thrive, while microbes provides a healthier soil environment. 5. Rhizofiltration. It is a water remediation technique that involves the uptake of contaminants by plant roots. Rhizofiltration is used to reduce contaminations in nature, wetland, and estuary area. We can see an overview of phytoremediation application. Overview of phytoremediation application. Techniques: phytoextraction, plant mechanism, uptake and concentration of metal via direct uptake into the plant tissue with the subsequent removal of water, surface medium, soil. Phytotransformation, plant mechanism, plant uptake and degradation of organic compounds, surface medium, surface water and groundwater. Techniques: phytostabilization, plant mechanism, root exudates, causes metal to precipitate and becomes less available. Surface medium, soil and groundwater and maintaining. Technique: phytodegradation, plant mechanism, enhances microbial degradation in rhizoids. Surface medium, soil, groundwater within rhizosphere. Techniques: rhizofiltration, plant mechanism, uptake of metals into the plant roots. Surface mechanisms, surface water and water pumped. Techniques: phytovolatilization, plant mechanism, plant evapotranspirate selenium, mercury, and volatile hydrocarbons. Surface medium, soil and groundwater. Techniques: vegetative cap, plant mechanism, rainwater is evaporates transpirated by plants to prevent leaching contaminants from disposal site. Surface medium is soil. Some plants used for phytoremediations are alpha-alpha symbiotic with hydrocarbons degrading plant. B. Transgenic Arabidopsis carries a bacteria genes that transforms mercury into a gaseous state. C. Bamboo family accumulates silica in its stalk and nitrogen as a crude protein in its leaf. And D. Indian mustard Brassica Juncea accumulates selenium, sulfur, lead, chromium, cadmium, nickel, zinc, and copper. E. Chinese ladder fern Teres vittata accumulates arsenic. And F. Cottonwood with added E. coli gene accumulates mercury. G. Tomato and alphane pennycris accumulates lead, zinc, and cadmium. H. Poplar used in the absorption of pesticide. Atrazine. Some of the best house plants for filtering indoor air and the pollutants they filter includes A. Green spider plant, Chlorophytum comosum, formaldehyde. B. Mother-in-law tongue or snake plant, Sansevieria trifasciata, formaldehyde and benzene. C. Chrysanthemums, chrysanthemum species, benzene. D. Gerbera daceus, Gerbera species, benzene trichloroethylene. E. Varieties of philodendron species, Philodendron scadens, Philodendron domesticum, Philodendron celoium, formaldehyde. F. Varieties of Daraceans species, Daracean fragrans, Daracean diramensis, Daracean warnecki, and Daracean morginata, formaldehyde. G. English ivy, Hedron helic, benzene. H. Golden hotpost, Epiprimnum aureum, formaldehyde. And I. Peace lily, Spathiphyllum, formaldehyde, benzene trichloroethylene. J. Aloe vera, formaldehyde.